Hello, it's Keith here, and this is the 6th in the Hello World series. This week we're going to look at the Camputers Lynx. We're going to learn how to create a simple Hello World. We'll then look at a slightly extended version with a monitor that will show the registers and memory. We're also going to learn how to create a valid tap file for our emulator so that we can load our program and test it. Okay, so first of all, let's just see the program running. So here's our simple Hello World. Let's fire it up. And here it is. So you can see here, we've shown Hello World here. This is all of just the loading code, and we've returned to basic here. So this is how we can run our program. And this is the code we're going to be looking at. So how do we actually write a Hello World program on the Camputers Lynx? Well, it's relatively straightforward. The problem's the tape file, but the actual code is straightforward. So I'm starting my program at hexadecimal 6500. This seems to be a fairly nice starting point because anything lower than that is used by the operating system. So we've pretty much allocated as much memory as we can safely do so. So starting at 6500. Now, the first thing I'm doing is I'm writing a 0 byte to this memory address here. Why am I doing this? Well, I will show you. If I disable this, which we can certainly do, we have this rather annoying sound in the background. And what this is it seems the tape loading routine is actually affecting the sound, and it's setting it to a default noise. So I'm turning off that default noise, setting the sound level to 0, and that will solve that. But say that's a bit of an extra here. Not necessary, but I would say so important that I've put it in there. Next, what we're doing is we're showing stuff to the screen. Now, all of this relies on the print character routine. All we do to print the accumulator to the screen, or the character in the accumulator, is we do an RST8. This calls the memory address at hexadecimal 8. This could be called RST1 on some systems, but that will print a character to the screen. If we want to do a new line, start a new line, we just print character 13 to the screen. So very simple. Now, of course, once we can print a character to the screen, we can extend this and print an entire string. That's what we've done. We've got a little program here. All it does is it loads in characters from HL. In the case of the example here, we're loading HL with the string message. You can see it down here. And it prints each character to the screen until it gets to a character 255, which is the end of the line, and at that point it returns. So here we've got our print string routine that uses our print char routine, and that is how we get that Hello World onto the screen. But we can do a little more. In my multi-platform series, we learned how to create a simple monitor. We're not going to cover that today, but what this can do is it can show us the state of the system. Now, if we're just starting out on a new system, then we're going to need to learn how things are working. We might need to turn on graphics modes, test the joystick, test the sound, and in the early stages, we might make mistakes. We might need to just double check that we're doing things right. And it's quite helpful to be able to see the current state of the processor, the registers in the processor, and the current state of the memory to check that nothing's happening that we don't expect. And that's what we're doing here. We're using the monitor command here, called monitor, to show the registers, and we're using the memdumpdirect command to show 32 bytes of memory at hexadecimal 6500, which is the start of our program. So let's fire this up and let's see the result. Okay, so you can see we've still got the Hello World message, but now we've got these registers here. So we're showing A, F, B, C, D, H, L, and P, C. So we can see those main registers here. And that's useful if we've got a loop that maybe is running more times than we expected. Well, we can now see the state of BC if that's going to be related to the problem. And also here, you can see we've dumped some of the memory here. And this AF here, I believe, is this XOR command here. So this is actually the program we're running here. Now, that's all fairly straightforward. As I say, if you want to see exactly how we wrote this monitor code, then please see the multi-platform tutorials in which I covered that. But if you just want to run it, this example will run that fine, and then you can use this as a template to start building up something cleverer. Okay, so that's how we can actually write code. We just need to select a start address and put the code in, and we can just return to basic once we're done. The tricky thing is when it comes to creating the tape file. So how do we create a tape file? Well, how I'm creating it is I'm actually building the file up myself. I actually reverse engineered the file format, and then I've got a program that I created called Binary Tools, which will do certain byte modifications of files, and this allows me to build up the file correctly. Now, the header is relatively straightforward. There's 8 bytes, which are the file name. You can see them just here. Then you've got 1 byte, which is the type. In the case of executables, it's always going to be an M, machine code. Then we've got the length. Now this is the length of the program itself, and this excludes the header. So we need to calculate that. Then we've got the load point. Now that's effectively the org address. So in my example, I'm using 6500. If you were using 7000, you would want to change it, of course. But as I say, I'm finding that to be about the safest option available. Below that is system functions and the stack. So we don't want to go too much lower than that. We're going to have some trouble. Then we've got the program code in the middle. Now, the program code is what this all compiles to. Finally, after the program code, we've got a check digit. This is a sum of all of the bytes in the program code. It's a single byte though, so when it goes over 255, it rolls back to 0. So we need to count up all the bytes of the program code and put that. Then we have the execution point again. This might not be the same as the load point, but in my example it is. If the first few bytes of your program were data, I guess they'd be different, but I would suggest against that. And then finally, for reasons that aren't clear, the high byte of the execution point is duplicated. You can see that here. We've got hexadecimal 78 twice here, because in this example the execution point was 7800. But anyway, so yeah, that's what we need to create. So how can we do this? Well, you've got various options. You could do this in your assembler in some cases. You can calculate the length of your program code with a few labels. If you put one label at the start of your code and one at the end and subtract them, you will be able to calculate that. Some assemblers may be able to calculate check digits. WinApe can do that, for example, in some cases at least. But what I've decided to do is I've decided to just skip using the assembler altogether because it's too complicated and too unpredictable. If you're using a different assembler, it's definitely not going to work. So I created this program called Binary Tools. It's not just for the Camputers Lynx, it's my go-to function for when I need to do complex things to data files. So what we're doing is we're creating a file called program.bin, which is the assembly of the code we've seen just here. Now the assemble command is very straightforward. We're using old style VASM Z80 here. I'm specifying a few symbols here, but these are only for the version with the monitor. You don't need that. We're specifying a binary file. We're disabling case sensitivity, and we're also checking labels. What this does is if we've made a mistake and forgotten the tab, the return command here will be mistaken for a label. If we enable check labels, then if a label matches the name of a function, a command within Z80, then it's going to warn us. So hopefully we'll realize we've made that mistake and it will save us some debugging. So this is just compiling the binary file. It's really what we do with that binary file next that's important. First, we're making a copy of it. We're making 2 copies, and we're going to work on one, and then we're going to write to the other. So what we're doing is we are checksumming the program, and we're writing it to the end of program.build. The -1 tells it to write to the end here. And so effectively we're writing that byte just here, but we need to do it twice. So we're running this command twice. So each time we're calculating the conventional 1-byte checksum of the program and attaching it to the end of program.build. Next, what we're doing is we're calculating the length of program.bin, our source file, remember, and we're writing it to position 9 of a file called header.bin. Now this is a file that already exists on the system. It's basically this file here. We're patching in the new length of the file that we've created to position 9, and that's this position just here, just after the M here. So that is patching in the length, because of course the length is going to be changing all the time. Okay, and then the last thing we're going to do here is we're going to write in a 16-bit address here, 0065. That's in little endian, so it's backwards, 6500. And we're writing that to the end of the file, and then we remember duplicating that high byte. So effectively we're writing these 3 bytes just here. And then also we're patching that in to header.bin, because of course the load point also needs to be 6500. So if we were to change our program code, so we can try that here. Suppose we didn't want to load to 6500, suppose we wanted to load to 7000. Just change that. We'll change this as well, just so we can prove it. Now if we change this here to 70, and this to 70, and this to 70, hopefully, if I've done this right, So our program still runs, and now you can see our program has indeed loaded to hexadecimal 7000, and that's why having these monitoring tools are very helpful, because we can see our program code, we can see the program counter, we can confirm what we've done has really worked. It's loaded to the address and it's actually called at that address. So by modifying the header like this, we can easily change the position of our program code if that's what we need to do. But I'm hoping I've actually selected the best version for you, the best place to load it to. I think 6500 is the lowest safe point and gives us the most memory we can really work with. So there we go. So now we've created a valid header, the final thing we need to do is combine our header with our program code into a TAP file. And I just use the Windows DOS copy command. We specify /b, which means binary. We specify the first file, the header, the second file, program.build, which remember we've appended the call address to. And then we just combine those in binary to a new file, which we call program.tap. This is our tape file, and it's now in the complete format. We can specify it with the Jinx emulator just by specifying --run and the name of the TAP file. And this automatically starts the TAP file when the system loads. You notice I didn't have to type any load commands to load the program in. So that's a great way of getting our emulator to straight away load the program. Saves us a lot of time. And that's really all there is to it. Anyway, that's how we can get Hello World working on the Camputers Lynx. Now, we got Hello World working there, and we showed some text to the screen using the firmware, but it's quite slow, and to be honest with the Camputers Lynx, and generally in programming in general, I think, you're often best trying to write your own routines and avoiding using the firmware. But when you're in the early stages and want to just get something working really quickly, having something that's as simple as possible like this, which is just a handful of lines, especially if you're not using VASM as your assembler and you need to make bug fixes, maybe your version is using different commands for commands like db and things, maybe they're different. Having an ultra simple, very, very short program makes things easier to get started. And as I've said before, once you've got anything on the screen and once you can see the state of the registers, you can then start trying to turn on graphics modes, writing bytes to screen memory and seeing how that works. So hopefully this is enough to get you started if you're feeling adventurous and you want to go your own way. If you want more tutorials, I've got lots of Camputers Lynx tutorials. We've done a graphics font before, bitmaps and sound and things. So please have a look at my channel if you want to see more Camputers Lynx. Please like and subscribe if you found this interesting. We're going to be doing more Hello World in the future. Thanks for watching today, and goodbye.